Welcome to the third IB thermodynamics video. We'll be talking about gas laws, but we have to start with the definition of pressure. Pressure is force per unit area. Equation, pressure equals F over A. The units are newtons per square meter, which we call the Pascal. Now the Pascal is a very small amount of pressure, and therefore we'll usually measure pressure in kilopascals. Atmospheric pressure is, to give you an idea, is 101.3 kilopascals, so over 100,000 newtons per square meter. An example of this, you've got a cylinder with a movable piston, has a diameter of 18 centimeters, filled with gas at a pressure of 220 kPa. How much force does the gas exert on the piston? So F equals pressure times area, which is 2.2 times 10 to the fifth pascals, and the area is the area of the piston, which is pi r squared because it's circular. So 0.09 meters is the radius, and you get your calculator, and you find that this exerts about 6,000 newtons of force on the piston, which is quite large. So that's how you would use that. It's a very easy example. Now we need to talk about what's called the kinetic model of the ideal gas. So this is something we talked about a little bit last year. You saw it in chemistry, but just to quickly review, there are 4 assumptions in the ideal gas law. The first one is that the gas consists of many small molecules. And when we say small, we mean small compared to the distance between them. So they generally stay fairly far apart. Second, when they run into each other, the collision is elastic. The kinetic energy that comes off of the kinetic energy of the 2 molecules after the collision is the same as the kinetic energy of the 2 molecules before the collision. And also that includes not only molecule to molecule collisions, but also collisions where the molecule collides with the wall. It bounces off with the same energy it had before. Now the next thing is we say that molecules have no internal structure. That turns out actually to be equivalent to the idea that collisions are elastic, but the idea is that we're ignoring bonds in the atom and we're ignoring energy of oscillation within each molecule. We're just looking at the kinetic energy. So we're only looking at KE, kinetic energy, for the internal energy. And related to that, there are no long-range forces. So the molecules interact only in collisions is another way of saying it. And because there are no long-range forces, that means that there is no potential energy that we have to worry about. And the results of these 4 assumptions are actually very, very accurate in a lot of situations. And specifically, they're accurate when the densities are low, which is to say that the molecules are far apart, and also when temperatures are high. And when we say temperatures are high, what that means is high temperatures compared to the boiling point of the substance. So let's say you boil water in your kitchen, you've got a lot of water vapor there. Well, that is not an ideal gas because it's only slightly above its boiling point. But the air in this room, even though it's not at what we think of as a high temperature, it's actually fairly chilly right now, it's well above the boiling point of nitrogen and oxygen, because those have boiling points of somewhere around -200 degrees. And so when we say high temperature, it means high compared to the boiling point of the gas. Another thing we'll say, and this isn't an assumption, it's just there, is that pressure is the result of collisions with the wall. The reason that the gas exerts forces on its container is because little bits of the gas are running into the container walls and then bouncing off again. Now, one thing that we'll say is that because there is no potential energy, the temperature is proportional to the average kinetic energy of the molecules. So if the temperature is higher, the average velocity, or the average speed, is higher. So higher temperature means the average speed is larger. Doesn't mean every molecule is moving faster, but if you calculate the average is increasing. And if the average speed is larger, that means two things are going to happen. Number one, collisions will happen more frequently with the walls. The other thing is that when a molecule collides with the wall, it takes more force, it exerts more force. So there are more collisions, and there's also more force in each collision. The combination of those two means that the increasing the temperature will make the pressure increase. Another thing that we can say is that if you increase the number of molecules or you decrease the volume, so you're basically increasing the density, that's going to cause more collisions with the walls, which will in turn cause higher pressure. And the result is that if we look at the pressure is proportional to the number of molecules, n, divided by the volume, V, times the temperature. And then there's also a constant R that we call the ideal gas constant, which equals 8.314 joules per mole Kelvin. And N is the number of moles of gas. And the more common way of writing this is PV equals nRT, which I imagine you probably have seen more than you want to in chemistry, and you're pretty good at using it. It's not a difficult thing algebraically. However, I'm still going to do an example because IB will ask you about it, and you need to be prepared for that. Now let's say we've got an ideal gas. It's confined, that means it's in a container, and that means the number of molecules isn't going to change, they can't escape. It's at a pressure of 300 kilopascals. The temperature is increased from 27 degrees Celsius to 177 degrees Celsius. At the same time, the volume is doubled. The question is, what is the new pressure? Now, the first thing we have to recognize is that when we're using the ideal gas law, the temperature must be measured in kelvins. And 27 degrees Celsius, you add 273 to that, that's 300 kelvins. 177 degrees Celsius works out to be 450 kelvins. Now the other thing is, we'd like to say, well, new pressure is just nRT over V. The problem is we don't know what N is, and we don't know what V is. However, what we can say is that the number of molecules isn't changing, so the quantity PV over T, which is equal to N times R, is a constant. And that means that the initial pressure times the initial volume divided by the initial temperature equals those same quantities at the end of the change. And so if we do some algebra, the new pressure equals P1 times the ratio V1 over V2 times the ratio T1 or T2 over T1. Now P1 is 300 kPa. We don't know what the volume is, but we do know that the new volume is twice as much as the old one, so that ratio is 1/2. Now T2 we said is 450 kelvins, T1 was 300 kelvins, and when we work this out, the new pressure ends up being 225 kPa. So fairly straightforward. Now for the last thing on this video, we need to talk about how real gases can diverge from the behavior of ideal gases. Now, the first thing, if the temperature is close to the boiling point, what will happen is that the forces between molecules will become important. And that means you have potential energy and it breaks. The other thing is that real gases have internal structure, which means that they have bonds between atoms. Those bonds can oscillate. They can do things like spin, and you get rotational kinetic energy, all that kind of stuff. Now, the interesting thing about this is that it does deviate from some aspects of the kinetic theory of gases, but not the parts that we just learned. The ideal gas law still holds even if the molecules have internal structure. Just calculating energy is a bit different. And the third way in which real gases differ from ideal gases is that if pressures are very, very high, what happens is that you end up forcing the molecules to become close together. Which means that the assumption we made that the molecules are small compared to the distance between them is wrong. And at very, very high pressures, what happens is gases start to act a little bit like liquids. And there's actually something called the critical point, where at temperatures and pressures that are sufficiently high, there's no distinction between a liquid and a gas. You will not be asked to calculate anything near the critical point in this class. So you need to know the assumptions behind the ideal gas law. You should be able to explain qualitatively why PV equals nRT. You should be able to apply the ideal gas law, and you need to be able to explain how real gases can differ from ideal gases.